Hello there, and welcome to the Sleepy Science Society. I'm so glad you found your way here tonight. Maybe you've had a long day, or maybe you're the kind of person who finds comfort in stories of human discovery, in the quiet unfolding of mysteries that once seemed like magic. Either way, you're in the right place. Tonight's journey takes us through one of the most electrifying stories in all of science, through centuries of wonder, through sparks in the dark and flashes of genius that would eventually light up the entire world. And if these calm explorations help you unwind, or give you something fascinating to drift off to, consider liking and subscribing to the channel. It helps others find their way here too, one curious mind at a time. Now, settle in. Let your breathing slow, your muscles relax, and your mind wander back through time. Because tonight, we're following electricity itself, from ancient mysteries to modern miracles. From the first curious spark to the networks of power that hum through every wall of every building you've ever entered. This is the story of how we learned to capture lightning, to bend an invisible force to our will, and to reshape civilization in the process. And it begins, as so many stories do, in darkness and wonder. The ancient world's electric encounters. Long before anyone understood what electricity was, people noticed it. They couldn't help but notice it. It appeared in sudden, dramatic flashes during storms, streaking across the sky with terrible beauty and earth-shaking power. It crackled through the air on dry days, causing hair to stand on end and producing tiny sparks when metal touched metal. It was mysterious, unpredictable, and sometimes deadly. And for thousands of years, it remained completely beyond human understanding. The ancient Greeks were among the first to document something we now recognize as electrical phenomena. Around 600 BC, the philosopher Thales of Miletus noticed something peculiar about amber, that golden, fossilized tree resin that washes up along shorelines and has been prized for jewelry since prehistory. When rubbed with cloth, particularly wool or fur, amber developed an unusual property. It could attract lightweight objects, small bits of straw or feathers or papyrus, pulling them through the air as if by invisible threads. This wasn't a strong force, nothing dramatic or particularly useful, but it was undeniably strange. The Greeks called amber electron, and this word, carrying its ancient mystery forward through millennia, would eventually give us the term electricity. But the Greeks, despite their philosophical sophistication, had no framework for understanding what they were observing. They noted the phenomenon, recorded it, discussed it, but it remained a curiosity, a parlor trick of nature. They didn't know they were witnessing the movement of electrons, those tiny particles that compose the outer shells of atoms. They didn't know about atomic structure at all. What they were seeing was static electricity, the buildup and transfer of electrical charge through friction, a process called the triboelectric effect. When you rub amber with wool, electrons are transferred from one material to the other, creating an imbalance of charge. The amber, now carrying extra electrons, has a negative charge, and that charge exerts an attractive force on neutral or positively charged objects nearby. But all of this explanation would have been incomprehensible to Thales. He simply knew that amber, when rubbed, gained a mysterious attracting power. The phenomenon appeared in other contexts too. Lightning, of course, was impossible to ignore, though no one understood its electrical nature. Ancient peoples across cultures attributed lightning to divine action, to angry gods hurling weapons from the heavens. Zeus wielded lightning bolts. Thor commanded thunder and storm. These were forces far beyond human control, manifestations of cosmic power, and trying to understand them in natural terms seemed almost presumptuous. Yet even as mythology explained lightning in supernatural terms, some observers must have wondered if there was something more, some underlying principle connecting the great flashes in the sky with the small sparks that sometimes jumped between objects on dry winter days. For thousands of years, that's where the mystery remained. Observations accumulated slowly. In medieval Europe, scholars occasionally noted electrical phenomena, but they lacked the tools and conceptual frameworks to investigate systematically. The amber effect was known, occasionally mentioned in natural philosophy texts, but rarely studied. Lightning continued to strike, destroying buildings and killing people, an unavoidable hazard of existence. Ships at sea reported seeing strange electrical glows around their masts during storms. Eerie blue flames that seemed to dance along the rigging. Sailors called this phenomenon St. Elmo's fire, attributing it to divine protection, never suspecting that they were seeing electrical discharge in action, the air itself becoming ionized and glowing in the presence of strong electrical fields. The world remained, for the most part, in darkness about this fundamental force of nature. But that was about to change. The tools of investigation were being developed. The methods of systematic inquiry were being refined, and a new era was dawning, one in which natural philosophers would begin asking questions in new ways and demanding answers that could be tested, measured, and verified. The age of Enlightenment was approaching, and with it would come a revolution in understanding, a transformation that would take electricity from mythological curiosity to practical power source in less than 2 centuries. The Age of Enlightenment. Sparks of understanding. The 17th century marked a turning point in how humans investigated the natural world. The scientific revolution was underway, bringing with it new instruments, new methods, and new expectations. Natural philosophers, as scientists were then called, began designing experiments specifically to produce and study electrical phenomena. They built devices to generate electrical charge. They searched for patterns, for regularities, for laws that might govern this mysterious force. And slowly, methodically, they began to accumulate real knowledge. One of the early pioneers was Otto von Guericke, a German scientist and politician who lived in the 1600s. Von Guericke was fascinated by the nature of vacuum and by various mysterious forces that seemed to act at a distance. Around 1660, he constructed what might be called the first electrical generator, though it was a simple device by modern standards. He created a ball of sulfur about the size of a child's head, mounted it on an axle so it could rotate, and found that when he cranked the ball, causing it to spin rapidly, and simultaneously rubbed it with his hand, the sulfur developed a powerful electrical charge. Objects placed nearby would be attracted to the ball, then repelled after making contact. then attracted again in an endless dance. Von Guericke had created a reliable way to produce electrical charge on demand, and with this tool, he could begin systematic investigation. What von Guericke discovered was fascinating and puzzling in equal measure. The charged sulfur ball would attract lightweight objects, just like rubbed amber, but the force seemed stronger, more dramatic. He also noticed that electrical charge could be conducted through certain materials. A thread connected to the charged ball would itself become charged along its length, capable of attracting objects even at a distance from the source. This was an important observation, the first to hint that electricity was something that could move, could flow from one place to another through suitable materials. Though von Guericke didn't understand the mechanism, he had glimpsed one of electricity's most important properties, its ability to be transmitted. Following von Guericke, other investigators built their own electrical generators, each one a bit more sophisticated than the last. By the early 1700s, various experimenters had created machines using rotating glass spheres or cylinders instead of sulfur, devices that could produce impressive electrical charges when cranked by hand. These machines became popular demonstration devices in the salons and lecture halls of Europe. Natural philosophers would charge up their generators, then create spectacular displays, making sparks jump through the air, causing people's hair to stand on end, producing crackling sounds and the distinctive sharp smell of ozone. Electricity was becoming fashionable, a source of entertainment and wonder. But it was more than mere spectacle. Careful observers were noticing patterns. They found that some materials conducted electricity well, while others did not. Metals were excellent conductors, capable of carrying electrical charge from one place to another with little loss. Glass, silk, and many other materials were insulators, unable to conduct charge at all, but useful for storing charge or preventing its escape. The distinction between conductors and insulators would prove crucial for practical applications, though those applications still lay far in the future. One of the most important inventions of this period came in 1845, independently discovered by two different experimenters, German cleric Ewald Georg von Kleist and Dutch scientist Peter van Musschenbroek, from the city of Leiden. What they created, now known as the Leyden jar, was the first electrical capacitor, a device capable of storing electrical charge for later use. The basic design was simple but effective. Take a glass jar, coat the inside with metal foil, and coat the outside with the metal foil as well, leaving the two metal layers separated by the glass. Extend a metal rod through a cork or wooden stopper into the jar so it makes a contact with the inner foil. Now, charge up your electrical generator and touch the rod with the charged conductor. The charge flows into the inner foil, and because the glass prevents it from escaping, the charge accumulates, building up to surprisingly high levels. The Leyden jar was revolutionary because it decoupled the generation of electrical charge from its use. You could charge up a Leyden jar using your hand-cranked generator, then carry the jar across the room, across the building, even across the city, and it would still hold its charge, ready to release it on demand. When you connected a conductor between the inner and the outer layers, the stored charge would rush through in a single dramatic discharge, producing a powerful spark and a sharp crack of sound. The discharge could be strong enough to cause painful shocks or even knock a person down. In fact, European experimenters delighted in creating human chains, dozens of people holding hands, then connecting the chain to a charged Leyden jar, and watching as everyone jumped simultaneously when the shock passed through their bodies. It was entertainment, but it was also science, demonstrating that electrical charge could pass through the human body, that it could affect living tissue directly. With the Leyden jar, electrical experiments could become more sophisticated and more controlled. Investigators could store up charge, then release it in carefully designed ways, studying its effects. They could connect multiple jars together to accumulate even greater charges. They began to explore the properties of electrical discharge in different environments, through different materials, across different distances. The pace of discovery was accelerating. Among those caught up in this wave of electrical enthusiasm was a printer, writer, and civic leader from Philadelphia named Benjamin Franklin. Franklin had become interested in electricity after attending a demonstration by an itinerant lecturer. He was immediately fascinated, purchasing electrical apparatus of his own and beginning his own series of experiments. Franklin brought to electrical investigation a practical, systematic mindset and a gift for clear explanation. He would organize the confusing, often contradictory observations of electrical phenomena into a coherent framework, and, in the process, perform one of the most famous experiments in scientific history. But that story deserves its own chapter, its own moment in the spotlight, because what Franklin did with a kite, a key, and a thunderstorm would change not just science but the course of civilization itself. Benjamin Franklin. The kite, the key, and the revolution. Benjamin Franklin stands as one of the towering figures of the 18th century, known for his political achievements, his literary works, his civic contributions, and his scientific investigations. But among all his accomplishments, none captured the public imagination quite like his electrical experiments, and none had more lasting impact than his demonstration that lightning, that most terrifying of natural phenomena, was itself electrical in nature. Franklin began his electrical investigations in the 1740s, setting up equipment in his home and conducting experiments with Leyden jars and electrical generators. He was a methodical experimenter, keeping careful notes, trying variations, looking for patterns. From these experiments, Franklin developed what he called the single fluid theory of electricity, proposing that electrical phenomena resulted from an excess or deficiency of a single electrical fluid that could flow from one object to another. Objects with an excess of this fluid he called plus, or positively charged. Objects with a deficiency he called minus, or negatively charged. Though the theory wasn't entirely correct in modern terms, we now understand electricity in terms of electron movement rather than fluid flow. Franklin's terminology stuck, and we still speak of positive and negative charges today. But Franklin's theoretical work, though important, was not what would make him famous. What captured attention, what sparked imaginations, was his bold hypothesis about lightning. Franklin had noticed that electrical sparks had many properties in common with lightning. Both created bright flashes. Both made crackling sounds. Both seemed capable of starting fires or damaging objects they struck. The resemblance was striking, and Franklin wondered if perhaps lightning and the electrical sparks he generated in his laboratory were the same phenomenon, differing only in scale. It was a radical idea. Lightning was still widely regarded as divine action, as something fundamentally different from terrestrial phenomena. But Franklin, with his Enlightenment confidence in natural law, suspected otherwise. In 1749, Franklin outlined his thoughts in a paper, listing the similarities between lightning and electricity, and suggesting that an experiment could settle the question definitively. His proposal was straightforward in concept, though dangerous in execution. Erect a tall iron rod, he suggested, perhaps atop a church spire or other high building, and see if thunderclouds passing overhead would discharge their electrical content into the rod. If lightning was indeed electrical, the rod should draw electrical charge from the clouds even before lightning struck, and that charge could be collected in a Leyden jar for study. Franklin wrote up his proposal and sent it to colleagues in England for publication. The proposal made its way to France, where it sparked immediate interest. French natural philosophers, already enthusiastic about electrical experiments, saw Franklin's suggestion as a test that could be performed. In May of 1752, Thomas François d'Alibard, following Franklin's instructions, erected a tall iron rod at Marly-le-Ville near Paris. When a thunderstorm approached, d'Alibard was not present, but he had left instructions with an assistant, an ex-soldier named Coiffier. As the storm passed over, Coiffier followed his orders, approaching the rod with an insulated Leyden jar. To his shock and delight, sparks jumped from the rod into the jar with a crackling sound, and the jar became charged just as if it had been connected to an electrical generator. The experiment was a success. Lightning was indeed electrical in nature. News of the French experiment began spreading through European scientific circles. Back in Philadelphia, Franklin had not yet heard of d'Alibard's success. He had been waiting to perform his own version of the experiment, hoping to use the steeple of a church that was under construction. But the steeple was taking longer to complete than expected, and Franklin grew impatient. Then, sometime in June of 1752, possibly on the 10th, though the exact date is uncertain, Franklin had an idea. Why wait for a building? Why not use a kite to reach up into the storm clouds? A kite could be raised quickly, could reach considerable heights, and could be flown from an open field where there was no risk of damaging property if something went wrong. The details of what happened next come primarily from two sources: a brief account Franklin himself published in the Pennsylvania Gazette in October 1752, and a more detailed narrative written by Joseph Priestley in 1767, based on conversations with Franklin. According to these accounts, Franklin constructed a kite from a large silk handkerchief stretched across a frame of cedar strips. To the top of the kite, he attached a sharp metal wire to act as a conductor. The kite string was hemp, a material that would conduct electricity when wet. But crucially, at the bottom of the kite string, where Franklin would hold it, he attached a silk ribbon. Silk, unlike wet hemp, is an insulator. This silk ribbon would protect Franklin from the full force of any electrical discharge. He also attached a metal key to the hemp string just above the silk ribbon, so the key would be connected to the kite but insulated from his hand by the silk. Franklin waited for a suitable thunderstorm. When one began to approach, he and his son William went out into a field. Franklin raised the kite into the rising wind. The storm darkened overhead. Rain began to fall, wetting the hemp string and making it conductive. And then Franklin noticed something remarkable. The loose threads of the hemp string were beginning to stand apart from each other, repelling one another as if charged. He brought his knuckle close to the key, and a spark jumped from the key to his hand. Another spark, and another. The kite was collecting electrical charge from the storm clouds and conducting it down the string to the key. Franklin quickly connected a Leyden jar to the key and watched as the jar became charged, exactly as it would from his electrical generator. The experiment was a complete success. Lightning was indeed electricity. It's important to understand what Franklin's experiment did and did not prove, and what risks it did and did not entail. A common misconception holds that lightning actually struck Franklin's kite, that a full lightning bolt discharged down the string while Franklin held on. If this had happened, Franklin would almost certainly have been killed instantly. Lightning carries enormous amounts of energy, far more than enough to stop a human heart or cause fatal burns. What actually happened was much more subtle and much safer, though still risky. The kite and its wet string reached up into an electrically charged environment. Even without a lightning strike, the air near storm clouds contains electrical charge, and this charge was drawn to the pointed wire atop Franklin's kite and conducted down the wet string. The sparks Franklin observed were from this accumulated charge, not from a direct lightning strike. Even so, the danger was real. If lightning had struck near the kite, the results could have been fatal. Franklin was lucky, and not all experimenters who tried similar experiments were so fortunate. The following year, a scientist in St. Petersburg named Georg Wilhelm Reichmann was killed while attempting to replicate Franklin's work, struck by what may have been ball lightning during an electrical experiment. But Franklin survived, and his experiment had profound consequences. The news spread rapidly. In America and Europe, Franklin became famous, celebrated as the man who had brought lightning down from the heavens and proven it to be a natural phenomenon, subject to natural law, no different in kind from the sparks that could be produced in any laboratory. The philosophical implications were enormous. If lightning, long considered the weapon of gods, was merely electricity on a grand scale, then what other supposedly supernatural phenomena might also have natural explanations? Franklin's experiment became a symbol of Enlightenment values, of the power of reason and observation to penetrate ancient mysteries. And the practical implications were immediate and life-saving. If lightning was electrical, and if electrical charge was attracted to pointed conductors, then buildings could be protected by attaching metal rods to their roofs. These lightning rods, as Franklin called them, would provide a preferential path for lightning to follow, conducting the electrical discharge harmlessly into the ground rather than through the building itself. Franklin published his ideas for lightning protection, and within just a few years, lightning rods were being installed on buildings throughout the American colonies and Europe. The device was simple, inexpensive, and remarkably effective. For the first time in history, humans had a reliable defense against one of nature's most destructive forces. Franklin's lightning rod represents one of the clearest examples of how scientific understanding can translate directly into practical benefit. The theory was elegant. Lightning seeks the path of least resistance to ground, and a metal rod provides that path. The application was straightforward. Attach rods to structures, connect them to the earth, and let physics do the rest. And the results were dramatic. Buildings that would have been destroyed by lightning strikes survived unscathed. Lives were saved. Property was protected. Insurance companies eventually began offering reduced rates for buildings equipped with lightning rods. Franklin's work had taken electricity from curiosity to utility in a single leap. But Franklin's contributions extended beyond the lightning rod. His terminology for electrical phenomena, his careful experimental methods, his clear explanations helped establish electrical science as a legitimate field of study. Other investigators built on his work, performing their own experiments, refining theories, developing new applications. The foundation was being laid for what would eventually become electrical engineering, though that transformation still lay decades in the future. First, science needed to understand not just static electricity, the accumulation and discharge of electrical charge, but current electricity, the steady flow of charge through conductors. And that understanding would come from an unlikely source: a dispute about dead frogs. The dawn of current, Volta and Galvani. As the 18th century drew to a close, electrical science faced a curious problem. Investigators had become quite skilled at generating and manipulating static electrical charges, at storing charge in Leyden jars, at producing impressive sparks and shocks. But all of these phenomena were momentary. You charged your generator, accumulated charge, and released it in a single discharge. There was no way to produce a continuous, steady flow of electrical charge. No way to maintain an electrical current over time. This limitation meant that certain kinds of experiments were impossible, and certain applications couldn't be pursued. What was needed was a new source of electricity, something fundamentally different from friction machines and Leyden jars. That new source emerged from an argument between two Italian scientists, Luigi Galvani and Alessandro Volta, about whether dead animals could generate electricity. Luigi Galvani was a physician and anatomist at the University of Bologna. In the 1780s, while dissecting frogs in his laboratory, Galvani made an accidental discovery. He had prepared a frog's leg, stripping away the skin to expose the muscles and nerves, and had hung the leg on a brass hook. The hook was touching an iron plate. When the leg came into contact with the iron, something remarkable happened. The muscles contracted violently, causing the leg to twitch and jump as if the frog were still alive. Galvani was astonished. He had not applied any electrical charge, had not touched the leg with charged conductors. Yet the muscles had responded exactly as they did when stimulated by electricity from a Leyden jar. Galvani experimented further, trying different metals, different configurations. He found that the effect was most pronounced when two different metals were in contact with each other and with the frog's tissue. His interpretation of these observations was dramatic. He believed that animal tissues contained a special kind of electricity, which he called animal electricity, or galvanism. that was somehow released when different metals made contact with nerves. In Galvani's view, living things stored electrical charge in their tissues, particularly in their nerves and muscles, and this charge was the animating force of life itself. When he created a circuit connecting nerve to muscle through two different metals, he was allowing this stored animal electricity to flow, causing the muscle to contract. Galvani published his findings in 1791, and they created an immediate sensation. The idea that electricity might be the vital force animating living creatures was philosophically thrilling. It suggested a kind of unity between the living and the non-living, between biology and physics. And the experiments were easy to replicate. Anyone with access to a dead frog and two different metals could see the legs twitch and jump. Soon, electrical demonstrations featuring dead frogs were popular attractions across Europe. But not everyone accepted Galvani's interpretation. Alessandro Volta, a physicist at the University of Pavia, was skeptical. Volta had his own extensive experience with electricity and had made his own contributions to the field. He repeated Galvani's experiments carefully, and he noticed something Galvani had overlooked. The critical factor wasn't the frog's tissues, it was the two different metals. When Volta touched two dissimilar metals together, then touched his tongue to both of them simultaneously, he experienced a peculiar taste, slightly bitter and metallic, and sometimes a tingling sensation. No animal tissue was involved, yet something electrical was clearly happening. Volta concluded that the electricity was being generated by the contact between the two metals, not by the frog. The frog's leg, with its sensitive nerves and muscles, was merely acting as a detector, responding to electrical current that was produced by chemical reactions at the junction between the metals. This interpretation sparked a long and sometimes bitter debate between Galvani and Volta. At stake was not just a question of scientific priority, but a fundamental question about the nature of life itself. Was there a special vital electricity unique to living things, or were living organisms governed by the same laws of physics and chemistry as everything else? The debate could not be settled by argument alone. What was needed was decisive experimental evidence, and Volta set about providing it. In 1800, Volta announced his most important invention, the voltaic pile, the world's first electric battery. Volta had taken Galvani's observations about metals and frog tissue and abstracted away the biological component entirely. He created a stack, alternating discs of zinc and copper with pieces of cardboard soaked in salt water between each pair of metal discs. When he connected a wire to the top of the pile and another wire to the bottom, he found that electrical current flowed steadily through the wires, not just a single discharge like from a Leyden jar, but a continuous current that persisted as long as the pile remained intact. The chemical reactions between the metals and the salt water were generating electrical charge, and the stacked arrangement allowed those charges to accumulate, driving current through any conductor connected to the pile. The voltaic pile was revolutionary. For the first time, experimenters had a source of continuous electrical current. The implications were immediately apparent. Within weeks of Volta's announcement, scientists across Europe were building their own piles, connecting them to various conductors, observing the effects. They found they could decompose water into hydrogen and oxygen by passing current through it, the first demonstration of electrolysis. They could heat wires until they glowed by passing sufficient current. They could produce chemical changes in solutions, plate metal onto conductors, and generate magnetic effects. A new era of electrical science was beginning. Volta's invention proved decisively that Galvani's animal electricity was not a special vital force, but simply ordinary electricity generated by chemical reactions. The frog legs in Galvani's original experiments had been responding to current generated by the contact between dissimilar metals, brass and iron, with the frog's own tissue fluids providing the conducting medium for the chemical reactions. There was no mysterious life force, only chemistry and physics working together. And yet, Galvani's observations hadn't been entirely wrong. Living tissues do use electrical signals, particularly in nerve and muscle function. When a nerve fires, when a muscle contracts, these processes involve the movement of charged ions across cell membranes, creating electrical currents on a microscopic scale. Both Galvani and Volta had glimpsed important truths, even though their interpretations differed. The resolution of their debate, with Volta's chemical theory proving correct about the source of electricity, opened the door to both electrochemistry and to the eventual development of practical batteries, devices that would become indispensable to modern technology. But before electricity could become truly practical, before it could reshape civilization, scientists needed to understand not just how to generate current, but how current related to magnetism, how it could be transmitted over distances, and how it could be converted efficiently into useful work. These insights would come from a new generation of investigators, men who would bridge the gap between scientific curiosity and engineering application. And chief among these was an English bookbinder's apprentice who would teach himself to become one of the greatest experimental physicists of all time. Faraday and Maxwell. Understanding the field. Michael Faraday's story is one of the most inspiring in the history of science. Born in 1791 to a poor family in London, Faraday received only the most basic education. At age 14, he was apprenticed to a bookbinder, and it was there, surrounded by books, that his education truly began. He read voraciously, teaching himself chemistry, physics, and mathematics from the books he was binding. He attended public lectures on science whenever he could afford the admission. When he heard that the famous chemist Humphrey Davy would be giving a series of lectures at the Royal Institution, Faraday scraped together the money to attend, took meticulous notes, and later sent those notes to Davy along with a request for employment. Impressed by the young man's dedication, Davy hired Faraday as a laboratory assistant in 1813. It was the beginning of a scientific career that would revolutionize our understanding of electricity and magnetism. Faraday's early work at the Royal Institution involved assisting Davy with chemical experiments, but Faraday's interests gradually shifted toward electrical phenomena. In 1820, the Danish physicist Hans Christian Ørsted had made a startling discovery. Electrical current flowing through a wire could deflect a magnetic compass needle. This suggested a deep connection between electricity and magnetism, two forces that had previously been thought completely separate. Faraday was fascinated. If electrical current could affect a magnet, could a magnet affect electrical current? Could magnetism be converted into electricity? For more than a decade, Faraday pursued this question through countless experiments. His approach was methodical, almost obsessive. He would try an experiment, observe the results, vary the conditions, try again. He built coils of wire, arranged magnets in different configurations, searched for any hint of electrical current being generated by magnetic forces. For years, he found nothing. The effect, if it existed, was elusive. But Faraday was patient and persistent, and in 1831, his patience was rewarded. Faraday wrapped a thick iron ring with two separate coils of wire. One coil he connected to a battery, allowing current to flow through it. The other coil he connected to a sensitive galvanometer, a device for detecting electrical current. Faraday's hypothesis was that when current flowed through the first coil, it would create a magnetic field in the iron ring, and this magnetic field might somehow induce current in the second coil. He connected the battery and watched the galvanometer. The needle jumped, indicating a brief pulse of current in the second coil, then returned to zero. Faraday was puzzled. There was an effect, but only for a moment. He disconnected the battery. The galvanometer needle jumped again, this time in the opposite direction, then returned to zero. A second brief pulse of current. What Faraday had discovered was electromagnetic induction, one of the most important principles in electrical engineering. Current in the first coil created a magnetic field. But the second coil didn't respond to the magnetic field itself. It responded to changes in the magnetic field. When the magnetic field was increasing, as it did when the battery was first connected, the changing field induced current in the second coil. When the field was steady, no current was induced. When the field decreased, as it did when the battery was disconnected, current was induced again, but in the opposite direction. The key was change. A static magnetic field produced no effect, but a changing magnetic field generated electrical current. Faraday explored this phenomenon in dozens of variations. He found that he could induce current by moving a magnet near a coil of wire. He could induce current by moving the coil near a stationary magnet. He could induce current by rotating a copper disc between the poles of a magnet. In every case, the same principle held. Changing magnetic fields produced electrical current. This was the inverse of Ørsted's discovery. If electricity could create magnetism, then magnetism could create electricity. The two forces were not just related, they were two aspects of a single electromagnetic phenomenon. The implications were staggering. Faraday's discovery meant that mechanical motion could be converted into electrical current. Turn a magnet near a coil of wire, and you generate electricity. This was the principle behind the electrical generator, the dynamo, the device that would eventually make large-scale electrical power generation possible. Conversely, if current flowing through a wire could create magnetic forces, then those forces could be used to produce motion. This was the principle behind the electrical motor. Electricity could be converted to motion, motion to electricity, opening up possibilities for machines that could operate without steam engines or water wheels, machines powered by the invisible force of electromagnetism. Faraday was not content merely to discover these effects. He wanted to understand them deeply, to grasp the underlying principles. And here he made another conceptual breakthrough that would prove as important as his experimental discoveries. Faraday introduced the concept of the field. In his view, when a magnet or an electrical current existed in space, it didn't just act directly on distant objects through some mysterious action at a distance. Instead, it created a condition in the space around it, a field of force that permeated every point, even empty space. This field was real, physical, capable of storing energy and exerting forces. Other objects responded not to the magnet or current directly, but to the field. Move through the field, and you experience forces. Change the field, and you induce effects in conductors within the field. This was a radical idea, completely different from the Newtonian physics that dominated the 19th century. Newton's laws described forces as acting directly between objects. Gravity pulling one mass toward another across empty space. Faraday's fields were something new, a modification of space itself, a physical presence even where no matter existed. Not everyone accepted the concept immediately. Fields seemed too abstract, too far removed from concrete, measurable objects. But Faraday's experimental results demanded explanation, and the field concept provided that explanation elegantly and powerfully. The mathematical formulation of Faraday's insights came from James Clerk Maxwell, a Scottish physicist who took Faraday's qualitative descriptions of fields and translated them into precise equations. Working in the 1860s, Maxwell developed a set of 4 equations that described completely how electrical and magnetic fields behave, how they're generated by charges and currents, and how they interact with each other. Maxwell's equations were a triumph of theoretical physics, unifying electricity and magnetism into a single theoretical framework called electromagnetism. But Maxwell's equations revealed something even more surprising. When Maxwell worked through the mathematics, he found that his equations predicted the existence of electromagnetic waves, oscillating patterns of electrical and magnetic fields that would propagate through space at a fixed speed. He calculated that speed using known electrical and magnetic constants, and the number he got was 300,000 kilometers per second, exactly the measured speed of light. The implication was unavoidable. Light itself was an electromagnetic wave, a form of electromagnetic radiation. Electricity, magnetism, and light were all connected, all aspects of a single fundamental force. Maxwell had unified 3 seemingly separate phenomena: electricity, magnetism, and optics, into one comprehensive theory. Maxwell's prediction of electromagnetic waves was confirmed experimentally in 1887 by Heinrich Hertz, who managed to generate and detect electromagnetic radiation using electrical circuits. Hertz's experiments proved that electromagnetic waves behaved exactly as Maxwell's equations predicted, traveling at the speed of light, reflecting off surfaces, refracting through different media. The confirmation of Maxwell's theory was one of the great triumphs of 19th century physics, validating the field concept and establishing electromagnetism as one of the fundamental forces of nature. All of this theoretical progress, From Faraday's experiments to Maxwell's equations to Hertz's confirmation, created a solid foundation of understanding. Scientists now knew how electricity and magnetism worked, how they were related, how they could be generated and controlled. The stage was set for electrical engineering, for the transformation of scientific knowledge into practical technology. And that transformation would occur primarily in the United States, driven by inventors and entrepreneurs who saw in electricity not just a fascinating phenomenon, but the key to a new industrial age. Two men, in particular, would become the public faces of this electrical revolution: Thomas Edison and Nikola Tesla. Their rivalry, their competing visions for how electrical power should be generated and distributed, would shape the modern world. Edison's empire, the rise of direct current. Thomas Alva Edison was already famous by the time he turned his attention to electrical lighting. He had invented the phonograph, the first device capable of recording and playing back sound, and the invention had made him a celebrity. The Wizard of Menlo Park, as newspapers called him, seemed capable of producing miracle after miracle from his New Jersey laboratory. But Edison's ambitions extended beyond clever devices. He wanted to create entire systems, complete solutions to major problems. And in the late 1870s, the problem that captured his attention was lighting. In 1879, most lighting came from gas, from flames burning behind glass fixtures in streets and buildings. Gas lighting was adequate, better than candles or oil lamps, but it had significant drawbacks. Gas flames produced heat, smoke, and occasionally dangerous leaks. They couldn't be turned on and off instantly. They required continuous maintenance, regular cleaning of fixtures, constant supply of fuel. And they were expensive, practical only in cities where gas mains had been installed. Edison saw an opportunity. Electric lighting, he believed, could be superior in every way: cleaner, safer, more convenient, and ultimately cheaper. But to make it practical, he would need to solve a series of difficult technical problems. The first problem was the light bulb itself. Other inventors had created electric lights, passing current through various materials until they glowed. But these early bulbs burned out quickly, sometimes in minutes or hours. The materials either melted, oxidized, or simply disintegrated under the intense heat. Edison approached the problem systematically, testing thousands of different materials as filaments, the thin wire or fiber through which current would flow, heating it until it glowed. He tried platinum. He tried various forms of carbon. He tried bizarre materials: fishing line, coconut fiber, cork, even human hair. Each material was carefully tested, its lifetime measured, its light quality assessed. After more than a year of the methodical experimentation, Edison and his team found success with carbonized bamboo. A thin strip of bamboo, heated in an oxygen-free environment until it converted to carbon, proved remarkably durable. Sealed inside a glass bulb with the air evacuated to prevent combustion. These carbonized bamboo filaments could last for hundreds of hours, emitting a warm, steady light. Edison had his practical electric bulb. But a bulb by itself was useless. It needed current to operate, and that current had to come from somewhere. Edison needed to build an entire electrical system. Generators to produce current, conductors to distribute it, switches and controls to manage it, meters to measure it for billing purposes, and fixtures to deliver it to customers as light. He needed, in short, to create an electrical utility company from nothing. Edison built his first complete electrical lighting system at Menlo Park in 1879, demonstrating that the concept worked. He then set his sights on New York City, planning to build a central generating station that would supply electrical power to customers throughout a district of Manhattan. The station he built at 257 Pearl Street, completed in 1882, was the world's first commercial central power plant. Its massive steam engines drove electrical generators called dynamos, producing direct current at 110 volts. From Pearl Street, copper conductors ran underground through conduits to businesses and homes in the surrounding blocks, bringing electrical power directly to customers' premises. On September 4, 1882, Edison's chief electrician threw the switch at Pearl Street Station, and 400 electric bulbs lit up in offices of the New York Times and other nearby locations. It was a historic moment. For the first time, electrical power was being sold as a commodity, generated at a central location, and distributed through a network to paying customers. Within a year, Pearl Street Station was serving more than 500 customers, and Edison's system was being replicated in cities across America and Europe. The age of electrical power had begun. Edison's system was built around direct current, which we now abbreviate as DC. In a DC system, electrical current flows in one direction, from positive to negative, at a constant voltage. Edison chose DC for several reasons. His light bulbs operated on DC. Batteries produced DC, so customers could have backup power during outages, and most importantly, DC was well understood. Edison and his engineers knew how to build reliable DC generators, how to regulate DC voltage, how to design safe DC distribution systems. DC was the proven, practical choice. But DC had limitations, serious ones that would eventually doom it as a system for large-scale power distribution. The main problem was voltage. Edison's DC system operated at 110 volts, a relatively low voltage chosen because it was safe, low enough that accidental contact wouldn't normally be fatal, but effective enough to light bulbs brightly. But low voltage meant high current for a given amount of power, and high current meant significant power losses in the distribution wires. Copper conductors have resistance, and when current flows through resistance, energy is dissipated as heat. The amount of power lost is proportional to the square of the current. So, to transmit significant amounts of power over any distance using low-voltage DC, you needed very thick, very expensive copper cables. Even with thick cables, Edison's DC systems couldn't economically transmit power more than about a mile from the generating station. If you wanted to supply a large city with DC power, you needed multiple generating stations scattered throughout the city, each serving only the nearby area. This worked, after a fashion, but it was inefficient and expensive. There was a theoretical solution to the problem. Use higher voltage for transmission. Higher voltage means lower current for the same amount of power, which means much lower losses in the wires. You could transmit power efficiently over much longer distances. But this solution created new problems in DC systems. High voltage DC was dangerous, potentially lethal to anyone who came in contact with it. And there was no efficient way to change voltage in a DC system. You couldn't generate at one voltage, transmit at a higher voltage, then reduce to a safe low voltage for customers. DC didn't work that way. You generated at whatever voltage you wanted to deliver, and that voltage stayed constant throughout the system. This limitation meant that Edison's DC systems, while revolutionary, were inherently local. They couldn't scale up to serve entire regions from a single large power plant. They couldn't take advantage of distant power sources like waterfalls or coal mines. They were practical for dense urban areas, where customers were packed closely together, but impractical for suburbs or rural areas. Edison was building an electrical empire, but it was an empire with clear geographical limits. What was needed was a different approach to electrical power, a system that could efficiently transmit electricity over long distances, that could serve vast areas from centralized generators. That system existed, at least in theory, and it was called alternating current. But AE came with its own challenges, its own technical hurdles, and the man who would overcome those hurdles, who would make AC practical and scalable, was working at that very moment in Europe, visualizing in his mind's eye a rotating magnetic field that would change everything. Nikola Tesla, the visionary from Smiljan. Nikola Tesla was born in 1856 in Smiljan, a small village in what was then the Austrian Empire and is now Croatia. His father was a Serbian Orthodox priest. His mother, an unschooled but remarkably intelligent woman who managed the family household and invented small mechanical devices to ease her work. From both parents, Tesla inherited gifts that would shape his life. From his father, a love of poetry and literature. From his mother, a practical ingenuity and a remarkable visual imagination. But it was his own unique mental abilities that set Tesla apart from an early age. Tesla possessed what he described as a photographic memory, an ability to visualize objects and machines in complete detail, as vivid and clear as if they were physically present before him. This was not merely a strong imagination. Tesla could construct entire machines in his mind, examine them from all angles, mentally operate them, even run them for weeks of simulated time to test for wear and weakness, all without ever touching a physical component. When he eventually built the devices he had designed mentally, he found they worked exactly as his mental simulations had predicted. This extraordinary ability made Tesla both a visionary inventor and, in some ways, isolated him. He lived partially in a world of pure thought, of perfect mental images, sometimes struggling to compromise with the messy realities of physical implementation. Tesla studied engineering at the Austrian Polytechnic School in Graz, and it was there, in a physics demonstration, that his path first crossed with electricity in a profound way. A professor was demonstrating a Gram dynamo, a device that could work either as a generator, converting mechanical motion to electrical current, or as a motor, converting electrical current to mechanical motion. When run as a motor using direct current, The Gram dynamo used brushes, small contacts that rubbed against a rotating commutator, a segmented ring that switched the direction of the current in the motor's coils as they rotated. These brushes sparked constantly, wasting energy, creating noise, and wearing out quickly. Tesla, watching the demonstration, found the sparking brushes inelegant, wasteful. He asked the professor if there wasn't some way to build a motor without brushes, a motor that could run smoothly without all that sparking and friction. The professor dismissed the question. No, he explained, it was impossible. DC motors required commutators and brushes to function. There was no way around it. But Tesla wasn't convinced. The problem intrigued him. Surely there must be a better way. He turned the problem over in his mind, thinking about it during lectures, during walks, during every spare moment. What would a motor without brushes look like? How could you make a rotor spin without constantly reversing the current direction with mechanical switches? The answer came to him in 1882 during a walk through a park in Budapest. Tesla was reciting poetry, a passage from Goethe's Faust, when suddenly his mind assembled the solution with perfect clarity. He literally saw it, fully formed in his imagination, a motor using alternating current instead of direct current. In an AC system, the current reverses direction many times per second automatically, oscillating back and forth. If you arranged coils of wire around a central rotor and fed them with AC currents that were out of phase with each other, that is, currents whose oscillations were offset in time, the magnetic fields from those coils would not just turn on and off, but would rotate, spinning around the motor. And a conducting rotor placed in that rotating magnetic field would be dragged along, forced to rotate by the electromagnetic forces acting on it. No brushes, no commutator. Just smooth, continuous rotation produced by the natural alternation of the current itself. Tesla stood in the park, transfixed, watching in his mind's eye as the magnetic field rotated, as the rotor spun within it. He took a stick and drew the design in the dirt, sketching the arrangement of coils, the placement of the rotor, working out the details. This was the rotating magnetic field, the principle that would make AC motors practical. And, more than that, it was the key to a complete AC power system, one that could generate, transmit, and use electrical power more efficiently than any DC system. Tesla knew he had envisioned something revolutionary. Now he needed to build it. For the next several years, Tesla worked various jobs in the European electrical industry, all the while refining his mental designs for the AC motor. He worked for a telegraph company in Budapest. He moved to Paris to work for the Continental Edison Company, installing Edison's DC lighting systems throughout Europe. It was respectable work, but Tesla's mind was elsewhere, focused on the AC system he knew he could build if only he had the resources and opportunity. Colleagues in Paris suggested he should go to America, to New York, to meet Edison himself. Edison was the most famous inventor in the world, and he was hiring talented engineers for his expanding electrical empire. Perhaps Edison would appreciate Tesla's ideas, would provide the backing Tesla needed to develop his AC inventions. In 1884, Tesla boarded a ship to America. He arrived in New York with 4 cents in his pocket, a book of poetry, some technical drawings, and a letter of introduction to Thomas Edison. The letter, written by one of Tesla's employers in Europe, described Tesla enthusiastically. "I know two great men, and you are one of them. The other is this young man." Whether Edison was impressed by such a recommendation or simply needed skilled engineers, he hired Tesla to work at his Pearl Street generating station, redesigning DC generators and solving various technical problems. Tesla and Edison made an odd pairing. Edison was practical, earthy, driven by commercial success. He trusted empirical trial and error over mathematical theory. He worked long hours, driving his employees hard, focused on results. Tesla was theoretical, imaginative, driven by the elegance of his designs. He trusted calculation and visualization over endless physical tinkering. He worked intensely but irregularly, disappearing into thought. And crucially, Tesla believed in alternating current while Edison had committed his entire company to direct current. The partnership was doomed from the start. According to Tesla's later accounts, Edison promised him a substantial bonus if he could improve the efficiency of the DC generators at the Pearl Street station. Tesla threw himself into the work, redesigning the machines, and succeeded in making significant improvements. But when he claimed his bonus, Edison reportedly laughed it off as a joke, as merely American humor. Whether this account is accurate or embellished by later myth-making is unclear, but what is certain is that Tesla and Edison parted ways after only a few months. Tesla left Edison's company, disappointed and increasingly convinced that Edison's dedication to DC was misguided. For a time, Tesla struggled. He found himself digging ditches for $2 a day to survive, his engineering knowledge useless without capital to develop his inventions. But his fortunes changed in 1887 when he met two businessmen, Alfred S. Brown and Charles F. Peck, who agreed to finance the development of his AC motor. With their backing, Tesla founded the Tesla Electric Company and set up a laboratory in Manhattan. Finally, he could build the machines he had been visualizing for 5 years. Tesla worked feverishly, constructing motors and generators based on his polyphase AC system. He used multiple AC currents, typically 2 or 3, with their oscillations offset in time, in phase, in electrical terms. These currents, fed into separate coils arranged around a motor, created his rotating magnetic field. The motors worked exactly as his mental simulations had predicted, smoothly, efficiently, with no brushes or commutators to spark and wear out. Tesla filed for patents covering his entire system: AC generators, AC motors, transformers for changing voltage, even the layout of transmission lines. Between 1887 and 1888, he was granted more than 30 patents, a complete package for AC power distribution. The key to Tesla's system was the transformer, a device invented earlier by others, but which became crucial in AC systems. A transformer consists of 2 coils of wire wound around an iron core. AC current flowing through one coil creates an oscillating magnetic field in the core, and this oscillating field induces AC current in the second coil. If the 2 coils have different numbers of turns, the voltages in the 2 coils will be different, proportional to the ratio of turns. You can step voltage up or down with perfect efficiency using nothing but coils and iron. This simple device solved the transmission problem that plagued DC systems. Generate AC at a moderate voltage. Step it up to very high voltage for long-distance transmission. High voltage means low current means low losses in the wires. Then step it back down to safe low voltage for customers. With transformers, AC power could be transmitted hundreds of miles economically, something impossible with DC. In May 1888, Tesla presented his AC system at a lecture before the American Institute of Electrical Engineers in New York. The demonstration was impressive, showing motors running smoothly on polyphase AC, showing how the system could be scaled up for power distribution. In the audience was an engineer representing George Westinghouse, a wealthy industrialist who had made his fortune with railroad air brakes and was now looking to enter the electrical power business. Westinghouse immediately saw the potential of Tesla's system. If AC could transmit power long distances efficiently, it could unlock vast new markets, could bring electricity to areas Edison's DC systems could never reach economically. Westinghouse met with Tesla and negotiated to purchase the patent rights to Tesla's AC system. The deal made Tesla wealthy, at least on paper, and gave Westinghouse the technology he needed to compete with Edison. But more importantly for history, the deal set the stage for an epic technological and business battle, a confrontation that came to be known as the War of the Currents. On one side stood Edison and his DC empire, backed by major financial interests, defended by the most famous inventor in the world. On the other side stood Westinghouse and Tesla with their AC technology, technically superior but largely untested at scale, requiring massive infrastructure investment, and facing the challenge of overcoming public skepticism and Edison's fierce opposition. The outcome of this battle would determine how electrical power would be generated and distributed for the next century and beyond. And it would be decided not by rational technical analysis alone, but by public demonstrations, propaganda campaigns, and ultimately by which system could prove itself in the most visible, most impressive way possible: the War of the Currents. The conflict between AC and DC power systems wasn't simply a technical dispute between engineers arguing about the best way to distribute electricity. It became a bitter public battle, fought in newspapers and lecture halls, involving character assassination, deliberate misinformation, and even gruesome public demonstrations designed to sway opinion through fear. At its heart, the War of the Currents was about control of what everyone knew would be an enormously lucrative industry. Whoever established the standard for electrical power distribution would dominate that industry for generations. The stakes could hardly have been higher. Thomas Edison had a tremendous advantage at the start of the conflict. He was famous, respected, seen as a genius inventor whose previous successes spoke for themselves. His DC systems were already installed in cities around the world, representing millions of dollars of infrastructure investment. Many of the most influential businessmen and financiers had backed Edison's ventures and were not eager to see their investments threatened by a competing technology. Edison leveraged all of this, launching a public relations campaign designed to portray AC power as dangerous, unreliable, and unsuitable for use in homes and businesses. Edison's attacks on AC focused primarily on safety. He pointed out, correctly, that AC systems used much higher voltages than DC systems, typically thousands of volts for long-distance transmission. Contact with such high voltages would be instantly fatal. Edison staged public demonstrations where he used AC current to electrocute animals, dogs and cats acquired from local pounds, and even in a particularly notorious incident, a circus elephant named Topsy. These demonstrations were morbid and manipulative, designed to associate AC power with death and danger in the public mind. Edison's team coined the term electrocution, specifically to describe death by AC electricity, hoping the word would catch on and permanently taint Westinghouse's system. The propaganda campaign reached its most disturbing point when Edison's associates promoted the use of AC current for a new method of execution. New York State was searching for a more humane alternative to hanging for capital punishment, and Edison's camp suggested the electric chair, powered deliberately by AC current from a Westinghouse generator. The first execution using this method occurred in 1890 and was botched horribly, taking several minutes and multiple attempts to kill the condemned man. But perversely, even this disaster served Edison's purposes. Newspapers reported extensively on the gruesome execution, noting prominently that the device used the same AC current that Westinghouse wanted to install in homes across America. It was propaganda of the darkest kind, and Westinghouse was understandably furious at the association. But propaganda alone couldn't win the war of the currents. What mattered ultimately was performance, economics, and practical results. Could AC systems actually deliver on their promised advantages? Could they be installed safely and reliably at scale? Could they serve customers better than DC? These questions would be answered through high-profile demonstrations and competitions that captured public attention. The first major test came in 1893 at the World's Columbian Exposition in Chicago, a massive international fair celebrating the 400th anniversary of Columbus's arrival in the Americas. The exposition required an enormous amount of electrical power to light hundreds of buildings, to run fountains and machinery, to create the spectacular nighttime illumination that would be one of the fair's main attractions. A contract to provide this power would be both lucrative and a powerful demonstration of whichever technology was chosen. Both Edison's General Electric Company and Westinghouse's company submitted bids. Westinghouse, using Tesla's AC system, won with a bid significantly lower than General Electric's DC proposal. The exposition would run on AC power. Tesla and Westinghouse worked frantically to design and install the system in time for the fair's opening. They needed to build generators capable of producing huge amounts of AC power, to design distribution systems to carry that power throughout the fairgrounds, and to do it all on a tight schedule. Tesla, working as a consultant for Westinghouse, contributed technical expertise, helping design the generators and motors. When the exposition opened in May 1893, it was a spectacular success. More than 200,000 incandescent bulbs illuminated the buildings at night, creating what visitors described as a magical, almost otherworldly scene. The lights never flickered. The system ran flawlessly for the duration of the fair. Millions of visitors saw AC power lighting up the White City and came away impressed by its reliability and scale. Even more significant was the contract awarded in 1893 for the construction of a hydroelectric power plant at Niagara Falls. This project had been discussed for years. Niagara Falls represented an enormous source of potential energy, water pouring over the falls with tremendous power that could be harnessed to generate electricity. But how? An international commission studied the question, inviting proposals from engineers worldwide. Many proposals involved DC systems, but the limitations were obvious. DC couldn't transmit power efficiently more than a mile or so. If the generators were built at Niagara Falls, the power could serve only the immediate vicinity. To serve Buffalo, some 20 miles away, or to reach other cities, AC transmission was necessary. Westinghouse won the contract, again bidding Tesla's AC system. The project was massive, requiring the construction of generators larger than any built before, excavation of massive tunnels to channel water to drive the turbines, and installation of long-distance transmission lines to carry power to Buffalo and beyond. Construction took years. Tesla consulted on the generator design, ensuring they would produce the two-phase AC current his motors required. When the first generator went into operation in 1895, followed by the completion of the transmission system to Buffalo in 1896, it was a historic achievement. For the first time, electrical power generated at a distant source was being transmitted over substantial distances to serve a major city. The Niagara Falls plant produced more power than all of Edison's DC stations combined. It was a clear demonstration of AC's superiority for large-scale power distribution. The war of the currents was effectively over, though Edison's DC systems would continue operating in some cities for years. Westinghouse and Tesla's AC system had won through superior performance and economics. Edison eventually conceded, with his company General Electric, shifting to AC systems in later years. The victory was complete, and its effects would be lasting. The AC system, refined and expanded but fundamentally unchanged from Tesla's original design, became the global standard for electrical power generation and distribution. Today, essentially all large-scale electrical grids use AC power, transmitted at high voltages, stepped down through transformers for local distribution, powering homes, businesses, and industries worldwide. Tesla's rotating magnetic field, first visualized during a walk in Budapest, had reshaped civilization. But Tesla's contributions didn't end with the AC motor and power system. His restless mind continued producing invention after invention, some practical, some fantastical, some that seemed like pure science fiction but hinted at technologies that would eventually become real. In the years following his AC triumph, Tesla explored wireless transmission of power and information, experimented with high-frequency currents and strange electrical phenomena, and demonstrated devices that amazed and sometimes frightened observers. He became, in many ways, a public wizard, a figure associated with electrical marvels and futuristic visions. Some of his later work would prove foundational to modern technology. Other projects would fail spectacularly. But through it all, Tesla remained driven by the same vision: to harness electrical forces in ways that would benefit humanity, to make power abundant and freely available, to light up the world and connect all people through invisible waves. Tesla's later innovations and wireless dreams. Following his success with the AC power system, Tesla might have rested on his laurels, might have settled into a comfortable role as a celebrated engineer and inventor. But that was never Tesla's way. His mind was too active, too filled with visions of what electricity could become. In the 1890s and early 1900s, he pursued a series of ambitious experiments and inventions, some of which would prove crucial to the development of the modern technology, others which would remain tantalizingly out of reach. One of Tesla's most famous inventions from this period is the Tesla coil, first developed in 1891. This device was, in essence, a specialized transformer designed to produce very high voltages at high frequencies. Tesla's coils could generate hundreds of thousands or even millions of volts, creating spectacular electrical discharges. Long sparking bolts of electricity that arced through the air like artificial lightning. These demonstrations were visually stunning, and Tesla used them to great effect in public lectures, entertaining audiences while simultaneously illustrating principles of high-frequency AC current. But the Tesla coil was more than a showpiece. It was a research tool that allowed Tesla to explore the behavior of high-frequency electricity. He found that high-frequency AC current could pass through the human body without causing the painful shocks associated with lower-frequency current or DC, a phenomenon related to the skin effect where high-frequency currents tend to flow along the surface of conductors rather than through their volume. Tesla would stand on the stage with his coil operating, millions of volts coursing around him, electrical streamers emanating from his body demonstrating that it was safe, or at least survivable, under the right conditions. These demonstrations were as much performance art as science, but they captured imaginations and helped establish Tesla's reputation as a master of electrical forces. The Tesla coil found practical applications as well. It became an essential component in early radio transmitters, used to generate the high-frequency oscillations needed for radio communication. Even today, variations of the Tesla coil are used in radio and television equipment, in educational demonstrations, and in various scientific instruments. Tesla's high-frequency experiments also led him to investigate what would eventually be called radio waves, electromagnetic radiation, at frequencies suitable for wireless communication. Tesla's work with radio is a contentious topic historically. Guglielmo Marconi is commonly credited with inventing radio, and he received the Nobel Prize in Physics in 1909 for his development of wireless telegraphy. But Tesla's contributions to radio technology were substantial, and in some cases preceded Marconi's work. Tesla filed patents related to radio transmission as early as 1897, describing systems using tuned circuits to transmit and receive radio signals. These patents covered fundamental aspects of radio technology, including the use of specific frequencies for different transmissions to prevent interference, essentially the principle of radio channels. Marconi's early demonstrations of radio communication were impressive and commercially successful, establishing wireless telegraph links across increasing distances, eventually even across the Atlantic Ocean. But some of Marconi's key patents were later challenged as derivative of Tesla's earlier work. The dispute dragged on for decades. Finally, in 1943, shortly after Tesla's death, the U.S. Supreme Court ruled in Tesla's favor, voiding 4 of Marconi's key patents and acknowledging that Tesla's patents had priority. This vindication came too late for Tesla to benefit from it financially or reputationally during his lifetime, but it established for the historical record that Tesla had indeed made fundamental contributions to radio technology. Beyond radio, Tesla experimented with wireless transmission of electrical power, an idea that seemed then, and to some extent still seems now, almost magical. Tesla envisioned a world where electrical power would be transmitted through the air or through the earth itself, eliminating the need for wires, allowing power to be drawn from the environment wherever it was needed. He theorized that the earth itself could act as a conductor, that electrical oscillations established at one point could be detected at any other point on the planet's surface. If this were possible, a single powerful transmitter could, in principle, provide electrical power to receivers anywhere in the world. To test this vision, Tesla established a laboratory in Colorado Springs in 1899, attracted by the location's high altitude and frequent thunderstorms. There, he built an enormous Tesla coil, much larger than any he had constructed before, capable of generating millions of volts. The coil was housed in a specially built laboratory with a retractable roof, and it was connected to a 200-foot metal mast that served as an antenna. When Tesla powered up his coil, the electrical effects were dramatic. Sparks up to 135 feet long arced from the mast into the sky, artificial lightning visible for miles. Thunder from the electrical discharges could be heard 15 miles away. Nearby, electrical phenomena occurred spontaneously. Butterflies were surrounded by glowing halos of St. Elmo's fire. Horses received shocks through their metal shoes. Light bulbs glowed faintly without being connected to any power source. Tesla claimed significant success with his Colorado Springs experiments. He reported detecting electrical oscillations that he believed had traveled through the Earth and returned to his apparatus, suggesting that his theory of Earth-conducting power transmission was correct. He also claimed to have received signals that he thought might be from space, from Mars or another extraterrestrial source, though this claim was met with widespread skepticism. Modern analysis suggests Tesla was probably detecting natural radio emissions from lightning or possibly from astronomical sources, phenomena that were not understood at the time. But regardless of the interpretation of his results, the Colorado experiments established that very long-distance wireless transmission was at least theoretically possible, and that high-power electrical effects could be created and controlled. Energized by his experiments, Tesla conceived an even more ambitious project: a worldwide wireless power transmission system that would also transmit information. The centerpiece would be Warden-Clyffe Tower, a massive transmission facility to be built on Long Island, New York. Tesla secured financing from J.P. Morgan, one of the wealthiest and most powerful financiers in America, on the promise that the facility would enable wireless transatlantic telegraph communication, something that would have enormous commercial value. Construction began in 1901. Warden-Clyffe Tower was an impressive structure, a mushroom-shaped tower 187 feet tall, topped with a 55-ton metal cap designed to serve as a transmitting antenna. Beneath the tower, Tesla had workers excavate deep underground, creating a system of iron pipes driven into the earth to establish a conduction path for his power transmission scheme. Tesla's vision for Wardenclyffe extended far beyond simple telegraphy. He imagined it as the first node in a global system that would transmit not just messages, but electrical power, making electricity freely available anywhere in the world, drawn from the air by simple receiving devices. It was a utopian vision. Technology in service of human welfare, eliminating barriers to power and communication. But the project was plagued with problems from the start. Morgan, Tesla's primary backer, became concerned about the practicality and profitability of the scheme. When Marconi successfully transmitted a wireless telegraph signal across the Atlantic in 1901, using much simpler equipment than Tesla's elaborate tower, Morgan questioned whether Tesla's approach was necessary. Tesla's assurances that his system would be superior, that it would transmit not just messages but power, did not assuage Morgan's concerns. Rather, they deepened them. A system that provided free electricity to everyone was not a particularly attractive business proposition for an investor hoping to make returns. Morgan cut off funding. Tesla scrambled to find alternative financing, but he was never successful. Wardenclyffe Tower was never completed. It stood incomplete and unused for years, a monument to Tesla's vision, but also to the gap between scientific imagination and economic reality. Eventually, the property was sold and the tower demolished in 1917. Tesla's dream of wireless power transmission for the masses died with it. Yet Tesla's work on wireless transmission was not entirely fruitless. His demonstrations of remote control, using radio signals to operate a small boat from a distance, were foundational to the development of all remote-controlled devices, from simple toy cars to military drones to modern industrial robots. His experiments with high-frequency currents contributed to the development of diathermy medical equipment, which uses high-frequency electrical currents to generate heat in body tissues for therapeutic purposes. His Tesla coils remain in use for various applications, and his vision of wireless communication, if not wireless power transmission, became reality with the global proliferation of radio, television, cellular phones, and wireless internet. Tesla saw the future, even if he couldn't quite build all of it himself. Tesla's later years were marked by increasing financial difficulty and isolation. Despite his patents and his fame, he never managed his finances successfully. The royalties from his AC patents, which should have made him wealthy for life, were forfeited in a renegotiation with Westinghouse when that company faced financial troubles. Tesla spent money freely on his experiments and lived in expensive hotels, but his income dwindled. He became increasingly eccentric, developing obsessive behaviors, claiming to receive signals from extraterrestrial civilizations, proposing fantastical inventions like a death ray that could destroy aircraft at hundreds of miles distance, but which he never demonstrated convincingly. Tesla died in January 1943, alone in a New York hotel room, in debt and largely forgotten by the public. Only later would his contributions be fully recognized. The unit of magnetic flux density was named the Tesla in his honor. His name was given to Tesla, Inc., the electric car company, acknowledging his role in making electric motors practical. His inventions and his vision of an electrically powered world are now celebrated, studied, and built upon. And the AC power system he designed, refined by generations of engineers but fundamentally unchanged in principle, continues to deliver electricity to billions of people worldwide, fulfilling at least part of Tesla's dream of illuminating the world with electrical power. The legacy and modern world. The story of electricity's discovery and development, from Franklin's kite experiments to Tesla's AC system, is a story of how scientific understanding transforms into technological capability, and how technological capability reshapes human civilization. Within a span of about 150 years, from the mid-1700s to 1900, electricity went from mysterious curiosity to essential utility, from parlor trick to foundation of modern society. This transformation stands as one of the most dramatic and consequential in all of human history. Consider what the world was like before electrical power. Communication was limited by the speed of physical transportation. To send a message across a continent required that weeks of travel by horse or ship. To illuminate a space at night required fire, whether candles, oil lamps, or gas flames. Mechanical power came from muscle, from animals, from water wheels and windmills, or from steam engines burning coal or wood. Manufacturing was localized, limited by the availability of power and the difficulty of transporting goods. Most people lived their entire lives within a few miles of where they were born, bound to rural areas by agricultural necessity, because cities could not sustain large populations without modern infrastructure. The world moved at the pace of walking horses and sailing ships. Electrical power changed all of this, not immediately, but inexorably. The electric telegraph, developed in parallel with early electrical science, made near instantaneous long-distance communication possible for the first time in human history. News that would have taken weeks to cross oceans could now arrive in hours or minutes. The telephone, building on telegraph technology, brought voice communication across similar distances. These technologies began knitting the world together, creating connections and dependencies that transcended geography. Electric lighting transformed cities. Streets could be safely lit at night, extending the productive day. Buildings no longer needed windows in every room for daytime light. Interior spaces could be illuminated electrically. Work could continue around the clock in factories. The dangerous, smoky gas lighting of the 19th century gave way to clean, safe electric bulbs. Public spaces became safer, more inviting, more active. But it was the electric motor, Tesla's invention refined by countless engineers, that perhaps had the greatest impact. Electric motors could be installed anywhere electricity could be delivered, providing mechanical power on demand without smoke, without fire, without the massive infrastructure of steam engines. Factories filled with electric motors, each machine powered independently, allowing flexible factory layouts and eliminating the dangerous overhead shaft and belt systems that had powered industrial machinery in the 19th century. Electric elevators made tall buildings practical, leading directly to the modern city skyline. Electric streetcars and subways transformed urban transportation, allowing cities to spread over larger areas, suburbs to develop, workers to live farther from their workplaces. Electric refrigeration, electric appliances, electric heating, and cooling. Each innovation made possible by electrical power, each changing how people lived. The AC power system that emerged victorious from the War of the Currents proved capable of scaling to enormous sizes. Individual power plants could serve entire regions. Transmission lines could carry power across continents, from sources to users hundreds or thousands of miles away. Hydroelectric dams could generate clean power from falling water. Coal and natural gas could be burned at centralized power plants, their pollution concentrated in areas away from population centers rather than distributed throughout cities. Nuclear power plants, developed in the mid-20th century, could generate enormous amounts of electricity from tiny amounts of fuel. All of these generating technologies fed into the same AC power grid, the same system of transmission lines, transformers, and distribution networks descended directly from Tesla's design. The spread of electrical grids across the developed world in the 20th century stands as one of the great infrastructure projects in human history, comparable to the building of road networks by ancient civilizations, or the construction of canal systems during the Industrial Revolution. In the United States, the Rural Electrification Act of 1936 brought power to millions of farms and small towns that private utility companies had ignored as unprofitable. Similar programs in other countries extended electricity to previously unserved populations. By the end of the 20th century, electrical power had become so fundamental to modern life that its absence defined poverty and underdevelopment. Access to electricity correlated with education, health, economic productivity, and quality of life, and the electrical revolution continues. Today's world is incomprehensible without electricity. The digital revolution, the development of computers and the internet, runs entirely on electrical power and electrical signals. The billions of transistors in a modern computer processor are tiny electrical switches, turning on and off millions of times per second. The information flowing through the internet is encoded in electrical signals in wires or in optical signals in fiber cables, which are themselves generated and detected by electrical devices. Smartphones, satellites, medical equipment, transportation systems. Nearly every aspect of modern civilization depends fundamentally on electrical power and electrical technology. Renewable energy systems, increasingly important as society grapples with climate change, are fundamentally electrical technologies. Solar panels convert sunlight directly to DC electricity, which is then converted to AC for feeding into the power grid. Wind turbines use Tesla's principles of electromagnetic induction, spinning magnetic fields inside wire coils to generate AC current. Energy storage systems, the modern descendants of Volta's pile, use advanced battery chemistry to store electrical energy for use when generation is low or demand is high. The transition to sustainable energy is, at its core, an electrical engineering challenge, building on the same physical principles that Franklin, Volta, Faraday, and Tesla explored. Recognition of Tesla's contributions has grown tremendously in recent decades. For much of the 20th century, Tesla was somewhat forgotten, overshadowed by Edison in popular consciousness and by more recent inventors in scientific circles. But renewed interest in Tesla's life and work, driven partly by his fascinating personality and partly by growing awareness of his fundamental contributions, has restored his reputation. He is now widely regarded as one of the greatest inventors in history. A visionary whose ideas and designs shaped the modern world in ways he might not have fully anticipated, but would surely have approved of. The contrast between Edison and Tesla as historical figures remains instructive. Edison, practical and business-minded, focused on inventions that could be immediately commercialized, that solved clear problems for paying customers. His approach was empirical, trying countless variations until something worked, then refining it for production. He built a successful business empire, became wealthy, and died famous and honored. Tesla, theoretical and idealistic, focused on inventions that he believed would benefit humanity, that would make power and communication universally available. His approach was to visualize perfect solutions, to understand principles deeply, then to implement those solutions with elegant efficiency. He struggled financially, died in relative obscurity, and only posthumously received full recognition for his contributions. Both approaches have value. Both men contributed enormously to electrical technology. Edison's DC systems, though ultimately supplanted by AC for power distribution, found lasting applications in batteries, in electronic devices, in any situation where smooth, constant current is needed. Edison's methodical, business-focused approach to invention became a model for industrial research laboratories. Tesla's AC system became the global standard for power generation and distribution. His theoretical insights into electromagnetic phenomena influenced generations of electrical engineers. His visionary approach, imagining revolutionary applications and then determining how to build them, continues to inspire inventors and entrepreneurs. Closing reflection. And so we arrive at the end of our journey through the discovery of electricity, from ancient observations of amber's attraction to the global power grids that now illuminate entire continents. It has been a journey through centuries of human curiosity, ingenuity, and perseverance, a story of how mystery becomes knowledge and knowledge becomes power. We began in darkness and wonder, with ancient peoples noting strange phenomena they could not explain. Sparks jumping on dry days, lightning splitting the sky. We saw how the Age of Enlightenment brought systematic investigation, how experimenters like Otto von Guericke and the inventors of the Leyden jar began to produce and store electrical charge reliably, turning electricity from occasional curiosity into reproducible phenomenon. We watched Benjamin Franklin fly his kite into a thunderstorm, proving that lightning was electricity and immediately applying that knowledge to create lightning rods that would protect buildings and save countless lives. We followed the dispute between Galvani and Volta, resolved when Volta created the first battery and demonstrated that electricity could be generated by chemical reactions, providing for the first time a source of continuous current, we explored Michael Faraday's patient experiments that revealed electromagnetic induction, showing that magnetism could generate electricity and electricity could generate magnetism, establishing the principles on which all modern generators and motors are based. We saw how James Clerk Maxwell took Faraday's intuitions and transformed them into precise mathematical equations, revealing that light itself was an electromagnetic phenomenon and predicting the existence of radio waves. We entered the industrial age with Thomas Edison, who built the first complete electrical power system, generating current at a central station and distributing it through a network to customers who used it to light their homes and businesses. We saw the limitations of his DC system, unable to transmit power efficiently over long distances, requiring multiple generating stations to serve even a modest city. And then we met Nikola Tesla, the visionary from Smealjan, who visualized a rotating magnetic field and from that vision designed an entire AC power system, motors without brushes, generators more efficient than their DC counterparts, transformers to step voltage up and down, making long-distance transmission economical and practical. We witnessed the war of the currents, the bitter struggle between DC and AC for dominance, resolved ultimately when AC proved its superiority at the Chicago World's Fair and at Niagara Falls. We followed Tesla into his later experiments, his spectacular demonstrations with Tesla coils, his contributions to radio technology, his ambitious but ultimately unsuccessful attempt to create a worldwide system of wireless power transmission. We saw a mind that never stopped imagining new possibilities, that saw electricity not just as a commodity, but as a transformative force that could unite humanity and elevate civilization. Throughout this entire story, from Franklin to Tesla and beyond, we see a pattern that characterizes so much of scientific and technological progress. It begins with observation of something strange, something that doesn't fit existing understanding. It proceeds through systematic investigation, through experiments designed to isolate phenomena, to measure effects, to establish patterns. It advances through theoretical insight, through the formulation of principles and laws that explain the observations and predict new phenomena. And it culminates in practical application, in the design of devices and systems that harness the newly understood forces to serve human purposes. This pattern repeats throughout the history of science. It is how we have come to understand gravity, thermodynamics, chemistry, nuclear physics, and countless other domains of knowledge. And in each case, the progression from mystery to mastery transforms human capability, changes what is possible, reshapes civilization. But few examples are as clear, as dramatic, or as consequential as the discovery and development of electrical technology. Today, as you lie here drifting towards sleep, electrical currents are flowing through the walls of your room, powering devices, maintaining temperature, perhaps charging a phone nearby. The same principles that Franklin glimpsed when sparks jumped from his key, that Volta demonstrated when he stacked dissimilar metals, that Faraday revealed when he moved a magnet near a wire, that Tesla embodied in his rotating magnetic field. These principles are at work right now, continuously, invisibly, reliably. The world hums with electricity, with power flowing through cables, with motors spinning, with lights glowing, with signals carrying information at the speed of light through networks that span the globe. And this electrical world, this civilization built on invisible forces flowing through wires, exists because human beings were curious, because they asked questions and pursued answers, because they were not satisfied with mystery but demanded understanding. It exists because Franklin was willing to fly a kite into a storm, because Faraday was willing to spend years searching for electromagnetic induction, because Tesla was willing to imagine an AC motor even when experts told him it was impossible. The story of electricity is, ultimately, a story about human potential, about what we can achieve when we combine curiosity with rigor, imagination with perseverance, theoretical insight with practical application. It is a story that continues because electrical technology is not finished, is not complete. New discoveries await. New applications will emerge. Solar panels and wind turbines, electric vehicles and power storage systems, quantum computers and artificial intelligence all represent the continuing evolution of electrical technology. The next chapters in a story that began with amber attracting straw and continues with the most sophisticated technology humans have ever created. If you found something fascinating in tonight's journey, something that sparked your curiosity or helped you see the world a bit differently, I hope you'll consider liking this video and subscribing to the Sleepy Science Society. Every like helps the channel grow, helps these stories of science and discovery reach more people who might find comfort in knowledge and wonder in understanding. And subscribing ensures you won't miss future journeys through the universe's mysteries and humanity's achievements. For now, let yourself rest. Let the story of electricity settle into your mind like sediment, becoming part of the foundation on which you understand the world. Close your eyes and imagine, if you like, the vast network of power flowing around you, through cities and across continents, a circulatory system of civilization, pulsing with AC current at exactly 60 cycles per second in North America, 50 cycles per second in most of the world, a global heartbeat that powers modern life. And as you drift into sleep, remember that you are a part of this story too. You are a beneficiary of centuries of scientific progress, living in a world transformed by discovery, illuminated by human ingenuity. The electricity that powers your world is the same electricity that crackled from Franklin's key, that flowed from Volta's pile, that spun Tesla's motors. It connects you to that history, makes you a participant in the continuing story of what electricity can become. Sleep well, dream softly, and perhaps, in your dreams, you might glimpse some mystery yet to be solved, some new understanding waiting to be discovered, some future application of electricity that would amaze even Franklin and Tesla. Because the story is not finished. It continues, night after night, discovery after discovery, building on what came before, reaching toward what might yet be. Good night.